This video explains the fundamental concept of the stiffness method for a simple one-dimensional rod element, which is a core part of the finite element method. It's a foundational topic in structural engineering and civil engineering. Consider the deformation of a rod subjected to both a temperature change and an axial force, F. It shows the rod's length along the x-axis. L is rod's original length. L0 is the length after a change in temperature. This is the length of the rod before the force F is applied. L1 is final length of the rod after both the temperature change and the axial force F have been applied. Initial strain in a rod due to a temperature change is defined as the change in the rod's length caused by the temperature variation, divided by its original length. The total, or final, strain is defined as the overall change in the rod's length, resulting from both the temperature change and the applied axial force, divided by its original length. If a rod is linearly elastic, its deformation due to external forces is governed by Hooke's law. Stress is defined as the internal force per unit cross-sectional area. It represents the intensity of the internal forces distributed within the material. For a rod, stress is calculated as the ratio of the applied force F to the cross-sectional area A, where F is the applied force and A is the cross-sectional area. For many materials, the relationship between stress and strain is described by Hooke's law, which postulates a linear elastic relationship between stress and the stress-induced strain. The equation is: stress is equal to the modulus of elasticity multiplied by the difference between the total strain and the initial strain. Hooke's law is connected with the concept of stiffness. Assuming no initial strain leads to a simplified form of Hooke's law stating that stress, sigma, is directly proportional to strain, epsilon, with the modulus of elasticity, E, as the constant of proportionality. To transform this stress-strain relationship into a force-displacement relationship, we multiply both sides of the equation by the cross-sectional area, A. Then, we multiply the right-hand side by the ratio of L to L, which is equal to 1, a common technique in engineering derivations used to rearrange terms. From the definition of stress, we know that force is a product of stress and cross-sectional area. From the definition of strain, we know that rod's length change is equal to strain multiplied by the initial length. By substituting these two relationships back into the equation, we get this final equation relates the applied force, F, to the resulting change in length, delta L. The term product of cross-section area and Young's modulus divided by the initial length is defined as the stiffness, K, of the rod, which is the constant that relates force and displacement. This derivation demonstrates that the stiffness of a rod depends on three factors. Cross-sectional area: a larger area makes the rod stiffer. Modulus of elasticity: a stiffer material has a higher E. Length: a longer rod is less stiff. The conclusion is that this stiffness, K, is the crucial link that connects the microscopic material properties, stress and strain, to the macroscopic physical behavior, force and displacement. We'll introduce two nodes at the ends of the rod, which we'll call node 1 and node 2. The initial, or undeformed, positions of these nodes are at coordinates x1 and x2. After the rod has been deformed by an applied force, the new positions of the nodes are x1 foot and x2. The initial, undeformed, length of the rod be calculated using the initial coordinates of the nodes L equals x2 minus x1. The length of the rod after deformation can be calculated using the final coordinates of the nodes L1 equals x2 prime minus x1 prime. The change in length, delta L, is defined as the difference between the deformed length and the original length. By removing the parentheses, distributing the negative sign to both terms inside the second parentheses, and then rearranging the terms to group the final and initial coordinates for each node, we obtain the following expression for the change in the rod's length, delta L. The change in position of each node is called its displacement. The displacement of node 1 is denoted by U1, and the displacement of node 2 is denoted by U2. Substituting these displacement expressions into the equation for the change in length gives the relationship between the rod's elongation, delta L, and the displacements of its nodes. From the relationships between force and change in length, and between change in length and nodal displacements, we can derive the force-nodal displacement relationship. The force at node 2, F2, is equal to the stiffness, K, multiplied by the relative displacement of the element. The relative displacement is the difference between the displacement of the end node, U2, and the start node, U1. From Newton's third law, the force at node 1, F1, is equal in magnitude and opposite in direction to the force at node 2. This is also expressed using the stiffness relationship. The two scalar force and displacement equations can be expressed in a more compact and organized matrix form, which is essential for the finite element method. This is the element stiffness matrix. It contains the stiffness coefficients that relate the nodal forces to the nodal displacements. This equation can be rewritten in a more compact form. U denoted the nodal displacement vector. K denoted the stiffness matrix. F denotes the nodal force vector. It is the fundamental equation for a single element in the stiffness method, and it serves as the basis for assembling a larger system of equations for a complete structure.